On to our next topic, fatigue failures, which is closely linked to and related with stress concentration. So we're going to cover them both here. So here, for instance, is a fatigue failure. That light doesn't seem to help or hurt. Helps a little maybe. Specifically, we'll be looking at how to identify that this is a fatigue failure. What is a fatigue failure? And why are they particularly insidious and dangerous? Here's a train wreck. So, fatigue failure is often associated with trains, planes, and automobiles. So, what is fatigue? Well, so first off, we need to have cyclic loading. So what does that mean? That means we're going to cycle, thus the word cyclic, cycle between tension and compression, or at least cycle between tension and no load. So with cyclic loading, we can get a yet new type of material failure that will be called fatigue, and it's characterized by the progressive growth of a crack through the material. Can't spell. So it's usually a progressive, usually slow, okay? Since it's associated with cyclic loading, we usually see this again associated with planes, trains, automobiles, etc., because you have lots of bolts, lots of shafts, and lots of connections that, when rotating, are experiencing a bending moment. What that does is, this is exaggerated, hopefully exaggerated, but it puts our shaft or our bolt or other connection under this bending moment, again while rotating. Well, okay, think about on the surface of this shaft, where is tension and where is compression? So our outermost fiber here, so here's the central axis, our outermost fiber on this side should be our max tension, and on this side should be our max compression. When the shaft rotates, the side of the shaft that is in compression will rotate around and be in tension. Then it rotates around and is in compression. Then it rotates around and is in tension, and so on and so on. So that makes our cycles. This is again a type of failure that can occur below the yield strength. Boy, you get out of strength of materials and you think, the yield strength is our safe point. We just design off of that, which is true. But then material science comes along and goes, oh, but we have these other insidious things that can destroy all of your work. Ah, okay. Anyway, so looking at where fatigue failure starts, it will start at what we call a crack initiation site. So, crack initiation sites occur at stress concentrations, which include threads. I'm going to try and write a little larger here. I realize it's getting a little small. Keyways, fillets, etc. Feel free to Google any of those. You don't know what they are. Or even just scratches can start a fatigue failure. So here we've continued to see surfaces of fatigue failures. We'll continue to see this pattern of lines, which is actually patterns of crack growth. Even here, where we're kind of moving at a different angle through this portion of a shaft, there's this line pattern that goes back and forth. So you're going to have these slides as a PDF file when I'm done, but also the original PowerPoint is on Canvas. Take a look at these and look at these patterns, because these are going to be important for identifying fatigue failures. So we'll look at a stress concentration example here in just a second. So initiating the start of a fatigue crack, which will start our failure, we'll have, and I'm just going to draw a round cross section, because most of our fatigue failed examples are in round parts, bolts and shafts. We will end up with some type of start point, and our crack will grow and radiate out from there. So it's going to be that linear pattern that we keep seeing. And eventually our component will overload and fail in a brittle fashion. So we'll leave that type of failure, we'll leave this pattern on our failed component. So we're going to look at this starting point, the initiation. We've got a stress concentration, which by the way is going to concentrate stress. Usually at an area of highest bending stress. Under tension, dislocations, we're talking about them again, will gather and pile up is not the most technical term, but it works. They get stacked up like cars piling up in a multi-car wreck. Okay, under tension, the dislocations will gather and pile up at the stress concentration. And what's this do? This starts a crack that will grow under tension. Cracks don't grow under compression. Alright. Started a crack. Okay. I can put this in compression as much as I want and it doesn't grow. Put it in tension and it grows. Okay? So there we go. So that's starting the crack. Now, let's get to this. What is a stress concentration? Well, it's a thing that concentrates stresses. Next. No. Okay. Here we go. Stress concentrations. Where do these exist? They exist at locations with geometric discontinuities. Aren't you glad I don't grade spelling? Okay, anyway, it's a fancy way of saying where the part, whatever our part is or our material is, changes shape or size. So, we have a round shaft, comes down, has a fillet in it, becomes a smaller shaft. We have a shaft, say looking at the cross section of it, that has a keyway cut in it. That is the worst looking shaft. Looks like a weird ham bone, but anyway, actually, that's supposed to look something like this. Okay, larger shaft, fillet, smaller shaft. There we go. Okay. So, you have a cross-sectional area and you've got just a little scratch in the part. You've got a shaft, and let's say there's a little notch cut in it for like a retaining ring or an O-ring or something to the effect. So anytime we're changing our geometry, we're deviating from here's a cylinder and it stays the same way, or doesn't have to be a cylinder, right? So this could be, it can be something. It's got a square cross section, and the corner might count because we've got a flat plate moving this direction essentially as part of the shaft, and a flat flat surface this way, flat surface this way, and suddenly they both end at a corner. That could count. Okay, so lots of different examples. For that matter, a piece of paper with a tear that's already in it, right? Okay, so anytime we change our shape or our size, there will be an equation that, at least for a first take on stress concentrations, is very straightforward, and it's going to be our stress effective equals a nominal stress times some factor. Okay, this is going to be a stress concentration factor. So stress concentration factor, it is geometry dependent. And it's always going to be greater than 1 for any real stress concentration. Nominal stress, this is your engineering 220, your strength of materials. It's your stress equals F over A type of calculation. Or it's your stress equals my over I, right, for a bending stress type of calculation. Okay, or it's your beam stress for beam buckling or whatever it is. Okay, so this would be your stress expected. With no stress concentrations. Your effective stress sometimes is also called stress actual or stress max. I try to say effective stress, but I switch around because at our geometric discontinuity, we're going to see a maximum stress, we're going to see an actual stress that the part sees, or it's an effective stress. All of the words work to describe it. This is going to be your stress with the stress concentration. I'm going to start abbreviating that. Included. Okay, let's do an example. So here we go. There are dictionary-sized books that just have charts like this. And mechanical and civil engineers used to have to do this by hand. Now we have wonderful things like finite element software that can do it for us, as long as we're paying attention to what we're doing and can input the information correctly. So we're going to make up an example, and I'll walk you through how to use this. And there are several homeworks already on Canvas. They either use this chart or a similar chart. So let's say we've got a shaft that reduces in diameter, and we want to find the effective stress here. So sigma effective. So let's see. We're going to come over here, make us a little room. We're going to find sigma effective when. Say large diameter is 1.1 inches. Small diameter is 1.0 inch. Radius is, let's do 0.05 inches. So that's the radius of this fillet here. And let's just give a nominal stress of 1,000 psi. Okay, so I'm choosing numbers that are easy to work with. So let's look at this chart and see what we have. Okay, first off, there's a formula here, but I've already given you the result of that formula. I'm giving you sigma nominal. I'm not giving you the bending moment. If I was giving you the bending moment, you'd have to come plug that in. Your C is actually your, I think Dr. Whitmer usually uses Y. I was taught Y, not C. But so my over I. You'd have to find your I and your Y and so forth for the smaller shaft, not the larger shaft, because we would normally expect the smaller shaft to have a higher stress than the larger shaft, so that would be our area of concern. Well, I'm giving that to you. Here I'm just saying it's 1,000. It's easy to work with. Okay. Well, let's look. This says R over D. Well, gosh, I guess we can do that calculation. Radius, 0.05 inches over small diameter is 1 inch. Gosh, I can do that math in my head. That's a dimensionless 0.05. I can divide by 1 all day long. So where is 0.05? Gosh, well, there's 0.1, 0.2. So looks like we're going up by 0.1. 0.05 is half of 0.1. So, hey, right here would be 0.05. So we're just following what's on the axis. R over D. Well, we did the math. We found a value. So this must be where we're supposed to be, is up and down this vertical axis somewhere. Well, then we've got this label over here, which is large diameter divided by small diameter. So what is that? That's 1.1 inch, again over 1 inch, which is a dimensionless 1.1. Hey, look at that. We've got a 1.1 here. That would be the third line up. So if we're on this third line up, and we're here, we intercept here. Which is associated with a y-axis value of 1.85, and that is labeled KT. That is our stress concentration factor. So now, let's see. I'm about out of room. There should be a blank slide after this for you guys to be working this on. What do we have? We have our formula. We've got sigma effective equals sigma nominal times KT. Well, gosh, let's see. That means sigma effective equals, I gave you a nominal stress, times 1.85, 1,850 PSI. What does that mean? That means on our shaft here, alright, so there's my artwork for the day. This can see 1,000 PSI bending stress across it. What do we see right here? We see 1,850, oops, if I can write, 1,850 PSI. What do we see here? I don't know, but it's less than 1,000. Because the shaft with the smaller diameter is 1,000. So shaft out here with the larger diameter is going to be less. Where are we going to fail? Well, gosh, this is where we're going to fail. We already know this. Okay, how do we already know this? If I got a piece of paper and I put a bend in it, alright, fold it over, bend it, regardless of if that's right in the middle and I offset it, where do you think it starts to tear at when we start to, this could take a while longer than what I intended it 2. There we go. Starts to tear where I already had a bend or a geometric discontinuity. If I've already got a tear in it, well, gosh, let's come over here and let's make, right, my highest torsion or bending should be in the middle between my fingers now. Well, but it comes over here. But, well, math says this should be the highest stress because it's in the middle, right? So if I've got a shaft simulated by a piece of paper and I'm putting a bending moment on it, my highest stress should be in the middle. But it's tearing off over here. Why? Where's the stress concentration there? And we all know the spot where it's already torn or breaking is the spot where a component is going to continue to tear or break. So we already knew what stress concentrations were. We just hadn't put any math to them yet. Chances are none of you have yet. So get into something like machine design. This becomes a much bigger thing. But this is a quick, good introduction to them. So if you've ever seen any of those guys that are like, their arms are as big as my head or my shoulder width or whatever, and they're like, I'm going to tear a phone book in half. They actually take the phone book and put a little cut with a hacksaw in it in the middle, and that gives them a stress concentration to start with that you can't see from the audience. Tearing a phone book in half is actually quite difficult. So anyway, that's using one of those charts. All right, so you see the chart, you see a bunch of lines, just look for little math things that you can do, like radius divided by diameter, one of the diameters divided by the other. Look for those on different places on the chart. That should get you to a curve somewhere off the x-axis and get you over to a stress concentration value. So some of the ones in the homework look different, but it's the same general concept. You should be able to figure it out. Okay, now here's a fun one. Let's jump into theory land a little bit. You might have asked, why in the world does this exist and where does the extra stress come from? So this is commonly explained like this, where you take your diameter of your shaft or whatever type of part we're looking with and say, well, imagine the stress is the flow of water. And when we get to the reduction in our size, this concentrates our stress. That kind of works, but stress isn't water flowing through a pipe. So this falls short, really, of explaining what's going on. Here's really what's going on. Let's imagine we're in a crystal structure. And we've got, all the way down to the crystal structure level, a geometric discontinuity. Right, so here's our nice cubic crystal structure. It continues on this way, down this way, and out this way. Okay, so this is an actual edge, this is an actual edge, and this is an actual edge. So imagine that on a much larger scale, this is our shaft right there where our fillet or our diameter is being reduced. We're right here at this edge, but all the way down to the atomic level. So we've got a larger diameter back here, and a smaller diameter over here. Okay, so now we're going to put a stress onto our part. So our atomic bonds are going to carry that stress, or that force. I'll just do this as a force. Force F. Force F. Force F. Force F. Okay, let's say it's a tensile stress, and we're evenly distributing it across our truss problem, right? So I'm not going to go to the effort to make this a real truss problem like out of statics or structures. It's just for the concept, okay? Well, so as we get further to the right, everything is still fine. Our bonds are carrying our stress. When we hit this edge, we have a problem. I have atomic bonds to the left here that have I'm saying stress when I'm writing F for force, but it's a stress or a force, okay? Normally there is an important distinction, but for what we're doing, we're just getting this concept across. Okay, so I've got this force on the atomic bond. Well, so this atom wants to reach out to the right and grab hold of the next atom through its bond and continue that force. But there's nothing out here. Aw, sad face. We're missing an atom. Well, what's it do? Well, the force doesn't just go away. It has to send that force somewhere. So what's it do? It goes to the only other atom it's connected to, at least in our two-dimensional drawing. This guy is facing the same problem. But look, he's got two forces pulling on him now. We're doubled up. This atom now has a whopping 3 piled up on him. This stress is concentrated. So what have we done by creating a geometric discontinuity here? We've forced our crystal structure to pull in directions that are not typical, not optimal for the force or the stress, and they are going to concentrate somewhere. If this bond here, which now has what? Triple-ish force on it, because this atom is getting pulled double from the top and from the side. Again, that's not exactly a stress like a truss type problem from statics, but close enough. Right? This bond breaks. Well, if this is too much force for this bond, what about this bond? Well, it's probably going to break too. So we've got one single weak link where the stress is concentrated. That's why you can take something like our shaft here, and it gets such a higher stress here. This is the worst case scenario. A 90-degree angle is the absolute worst case. Something with a fillet or a curvature is better. But that is why a stress concentration exists. That's what happens right here, all the way down to the crystal structure level. So, with that, and when we, let's go back to, let's see, what's a good picture? This one. We're going to go back to here. So let's say we've got geometric discontinuity here on our shaft. We've got a stress concentration. We're rotating this, and let's say it's in compression, and we rotate it around and it's in tension. Couple of things going on. Not only do we have a stress concentration that preferentially tries to start failure there on our part, but we've also got kinetic energy. So by now, if you've watched the impact lecture, I've already told you about how insidious kinetic energy can be when added on to what we think should be a static type problem. Well, because we've got a rotating part, we've got kinetic energy. It's mass that's in motion. We're adding an impact on top of our stress concentration every time that shaft spins around from being compression to tension. So there's a complex set of stress going on here. And that is what's going to make our fatigue crack grow. So the propagation, so what does that mean? That basically means it's a fancy scientific word used in materials to basically mean growth. So it's our crack growth. On the surface of our fatigue failure, we get this pattern that's called beach marks. Why is it called beach marks? Because it looks like sand on the beach. Yay, the name makes sense. Okay. So this isn't even at a microscope. This is just like a good cell phone camera or portable, like, click the button camera back when people would carry those around. Just with a good macro lens. So this isn't even under a microscope. But we see this wavy pattern. That wavy pattern is officially called beach marks. So each of those represents a period over time when the crack growth was occurring. So we'll have a point that starts that, and then the waves kind of that represent the crack's growth radiate out from there. So, and actually, if you were to stop and look at a fatigue failure before it's finished, we would find some of these completed, and then we would find good material still beyond that. So our propagation is our stress. That's not abbreviated, but there's a period there. Okay, stress concentration plus rotational kinetic energy when in tension. We rotate back around to compression, the crack growth stops. Rotate back around into tension, and the crack starts to grow again. So, to test this, we have what is called a rotating beam fatigue test. Okay, well, we've got a beam. That's our specimen. It's a beam shape. It's going to rotate, and we're going to look for fatigue. Rotating beam fatigue test. Real exciting, right? So this is kind of an artistic representation of one of these machines. There will be a YouTube video posted where I went and found some company demonstrating their instrument to do this. But basically, here's our bearing housings, right? So these are supposed to be two different variations of the same thing, right? So motor, high-speed motor, counter. These are the bearing housings. Just put BH for bearing housings. Here's our specimen, and it is under load, which creates a bending moment on our specimen. That creates tension on one side and compression on the other. And then we'll rotate this and count the number of rotations. And we'll look at how many times can I rotate this under a given stress before we fail in fatigue. The data generated by such an experiment looks like this. And so this is data from rotating beam fatigue tests. It is plotted on an SN curve. Okay, what is that? Well, here is stress, and this says cycles to failure, but you'll also see this labeled as number of cycles to failure. S for stress, N for number of cycles. Okay, SN curve, stress, number of cycles curve. So what we have here is each of these data points is a specimen failure. So all of those data points along there, and then we've plotted this sort of trend line through them. So each of those data points is associated with a stress and then a number of counts off the counter that motor rotated the specimen. Usually plotted on a log-log scale. It looks cleaner this way. So at essentially 0 cycles, which we can't really plot because log 0 is undefined, so they've got log of 1/4. It's less than 1 cycle. Okay, so it's basically 0. At just putting the material in tension and seeing when it fails, well, that's your tensile strength. That's your UTS, ultimate tensile strength. They've got the yield strength labeled here. And we can see that under low revolutions, we do tend to stay above the yield strength. So what is this? This is 10 squared down here. So we're looking at somewhere between 100 and 1,000 cycles. We tend to stay above the yield strength. So that's not too bad because we are usually designing off the yield strength. Here's our danger area where we are now failing below the yield strength. Now, here's the trick, okay? Are we really magically failing below the yield strength? No. Our yield strength is done off a tensile test. A tensile test is a highly idealized test where your stress is applied slow and steady and only in tension. So we're essentially eliminating kinetic energy, we're eliminating bending moments, we're eliminating a lot of things that happen in the real world in a tensile test. So once you throw in a stress concentration at that point that we are starting a fatigue failure, then is that point of stress concentration really below the yield stress? Probably not. It's difficult for us to go in and identify exactly what does every single scratch that may ever happen on a part, what's that going to do to the stress concentration and the stress before it happens. Well, we can statistically go make some guesses, but we can't see the future. So compared to a tensile test, we're below the yield stress. Well, so that's our go-to thing for what is the strength of material. That's what makes this dangerous, is that this adds complexity to our design. So, okay, anyway, Good news buried in here is we have this thing called an endurance limit. Okay, so let me just go over to the next slide. And we're going to look at two different things. We're going to look at a fatigue strength and endurance limit. So our fatigue strength is a stress level where the material survives without breaking for a specified in cycles. So if I come in here and I say, well, I want my part to last for at least 10 to the fourth power cycles. Here's 10 to the fourth power on my graph. I go up. I find our line or a data point, and I go over to the stress value. Where is that? It's at about 70,000 KSI. So, 70 KSI, 70,000 PSI. Big difference there. Okay. So, that is a fatigue strength. It lets me specify an approximate survival time for our part, and I can design the cross-sectional area or other geometry factors of the part so that my part fails at a specific amount of rotations. Okay, so our endurance limit this is cool. This is a stress level where we can stay less than, I'm not wording this great, but it gets the point across. And our material survives theoretically infinite cycles. Okay, so here we have essentially a flat line part on our graph. What that means is that if we go below this stress, I can theoretically keep going out in cycles and never fatigue fail. Okay, so that is the difference in a fatigue strength and an endurance limit. It's great that we have endurance limits. Let's pick a typical washing machine or a typical car. Where do we design to on this graph for all of our different parts? Say various shafts or moving parts either in the car or the washing machine or whatever. Do we design at a stress level down here so that our parts survive for infinite number of cycles? Or do we pick a fatigue strength where we go, well, it'll only survive for this many cycles and then my part fails, which means my washing machine or my car fails? What do you think? We are going to design differently depending upon the part. Most of our parts, especially ones that are not safety critical, are somewhere out here. Which means they are above our endurance limit, and they will fail. And they are designed to fail. So what does it mean if we're giving a fatigue strength? It means designed to fail. Now, we can be really quick to judge corporations. And we can go, they could do a better design and give me a product that never fails, at least not in fatigue. There may be other things that it will fail in, but at least not in fatigue. However, there's a couple of reasons that this isn't just corporate greed. Consumers, that's us, will typically purchase a cheaper product even with a lower warranty. Our society's rush to buy now, worry about it later, rather than to save and purchase a quality product, has created this and done it to ourselves. What companies have found out is if they offer a washing machine with a lifetime warranty, most people won't buy it. We have done this to ourselves, or at least a lifetime warranty on, say, rotating components, but not necessarily electronics, right? Well, eventually your electronics are going to go out anyway, so you might as well just buy a new washing machine. Well, then why design it to never fail in fatigue if the electronics are probably going to go out first? So this isn't just corporate greed. It is a way to save resources and offer a cheaper product that people want. The other issue, especially in something like automobiles, is we want to fail non-safety critical parts before we risk safety critical parts. So here's what that means. That means that on your car, truck, motorcycle, whatever it is, if you've got a steering column, hopefully you've got some kind of steering, you get a steering column. It's probably designed down here for stress, which means it should not fatigue fail. A lot of other parts may be designed at fatigue strength to fail. Maybe something in the fan, some of your different bearings on the fan belts, this belt, that belt, whatever, compressor in the AC. That stuff starts failing. It starts getting frustrating to fix, and eventually you replace the vehicle before some type of corrosion or unexpected event on the car that creates a scratch. Say some shade tree mechanic is working on it, dings your steering column with a saw and doesn't say anything about it, right? They don't know what's going to happen, and that can add factors that eventually fail a safety critical part. They are intentionally designing failure into a product to get you to try and replace that product before they anticipate a safety critical failure could happen. That's nothing to do with corporate greed, other than maybe they don't want to be sued, but they also don't want to see people get hurt. At least hopefully that's a motivating factor. So it's not just, well, we want you to buy new parts, so we're just going to design them to fail. It's not that simple. Yeah, sure, that's part of it. Okay, I'm sure that that's somewhere in the board meeting. Okay, whatever, however we want to say that. Okay, so endurance limit great. Here's one for 1045, just plain medium carbon steel. Aluminum, in general, we consider aluminum to not have an endurance limit. So, guess what? What do we make planes out of? Well, mostly aluminum. Okay. So, that creates some issues. Realistically, aluminum has an endurance limit. I think if you just took a bar of aluminum, attached it to a motor, and just started rotating it under its own weight, I don't think we would really expect that to fatigue fail, right? It's just aluminum's endurance limit is low enough that we often consider it to not have an endurance limit. So, if you've ever been on a plane, right? So here's our plane. Here's our nice little pilots, 6 feet apart, doing social distancing. Okay. There's our plane from the front. If you've ever sat and watched the wing, they actually rotate up and down, right? So the thrust that they're generating bends the wing up, but then it'll end up bending back down. And so the wings actually sit there and shake up and down. So I had a professor in graduate school that, well, maybe you've heard me mention this guy. This is the guy that would throw people's cell phones against the wall and say, like, I dare you to do anything about it. And then one day his cell phone rang in class and he turned around and went fair as fair and threw his own cell phone against the wall. Now, this was before the days of smartphones, but yeah. Anyway, interesting guy, super smart. Maybe just a little bit on the extra interesting side. Anyway, he liked to get on planes. He did this one time with a group of grad students going to a conference. And after the plane took off and the wings started bobbing up and down, he said, oh, this would be a great time to talk about the cracks that are in all the airplane wings and how they grow every time the wing bobs up and down. And he just loved to watch for the general people around him to start freaking out as he explained crack growth and how all the airplane wings have crack in them that are fatigue cracks, and they're all going to fall off someday if we don't recycle the planes. We take these things out of service way before they should fatigue fail. At least we're supposed to. But it's true. All of our aluminum parts that start experiencing cyclic loading, they're all going to have fatigue cracks. So, just part of the mechanical design that we have to worry about. Okay, let's get ready to wrap this up. Let's look at some data. This is not the greatest graph. So here I've got, these are A, B, C, D. Here's actually A, B, C, D written off to the side. Heat treated alloy steel, very high endurance limit relative to just a plain medium carbon steel. That'd be something like our 1045. Aluminum labeled as not having endurance limit. Cast iron, being an iron-based alloy, does have an endurance limit, but because of the nature of cast iron, it's a terrible endurance limit. So, just a relative comparison between materials. In general, the stronger the material is, usually the higher its endurance limit. So looking at characterizing a fatigue failure, so I've talked about how do we characterize an impact failure, tensile failures, right? We talked about ductile and brittle failures before the first test. Also creep failures. Now we're looking at fatigue failures. This is the general breakdown of the fatigue failure. It's labeled. We've talked about beach marks, initiation sites. There's a relatively smooth area with beach marks that is a wavy pattern. And then we'll have a rough area that is a final catastrophic, usually brittle failure. That's essentially a brittle impact failure. So, making comparisons here, we have final failure looks like this on a fatigue part. Here we can see this wavy pattern. So our beach marks or waves. Down here, we're looking at, here's a spot where some type of set screw appears to have been machined in there. It looks like there's some threads inside of that hole, and that's going to be our initiation. It's at a stress concentration. It's also on the outside of the part, so we're at our highest bending stress. Influencing fatigue. I already said we can pick stronger materials. Also tougher. Toughness can help. Right? Resistance to impact. So this is how much energy we can handle. This is how much stress we can handle. All right, so our ability to handle stress, our ability to handle kinetic energy. So we're selecting stronger, tougher materials. Also, surface finish. So, if we cannot design our part to simply be larger, if that's not effective, which a lot of times it's not, then here's our two primary ways of resisting fatigue failures. Polish the surface, select stronger, tougher materials. So looking at a 4063 quench and tempered steel to a Rockwell hardness of 44, giving just a plain grind, we give a surface roughness value. Let's not worry too much about that. It is a value from a test you can do where the numbers represent sort of the hills and valleys in the almost to the microstructural level of your part. So the higher the number, the rougher the part. We're given an endurance limit. Here's 91,300 psi. Machine lapped, which is a polishing method. Longitudinal grind added. Super finished with extra polishing. Another super finished with extra polishing. Well, as we get a smoother and smoother surface, so getting smoother. So this is going to be like a mirror polish down here. This is going to be rough up here. Notice we get a significant increase in our endurance limit. It's not like huge leaps and bounds, but this is significant. So otherwise, we go back to having to select a stronger but possibly more expensive material to get a better endurance limit. Something else to be concerned with is there is a, so here's stress, number of cycles, so this is an SN graph. Looking at a zinc-based alloy at different temperatures, there is an effect of temperature on our endurance limit. So endurance limit decreases with increasing temperature, right? So we see our increasing temperatures. So, and we see a decreasing endurance limit. At a really high temperature, it looks like we've eliminated the endurance limit even. So, reduced endurance limit. Okay, ending notes. Check. Announcements and discussions. You should have information up. I sent an email out about quizzes and exams. We'll have a quiz Tuesday the 14th is the plan. Or no, excuse me. Tuesday the 7th. An exam Tuesday the 14th. Another quiz Tuesday the 21st. It'd be nice to do our third exam, which we'll just do 3 exams. Our homework quiz is attendance, right? Be nice to do our third exam finals week on the 28th. That is not the normal time, so I realize that might be a problem. I was just thinking let's do something Tuesday at every time so that everyone's in the rhythm. Maybe that works for all but one or two people, and we might go ahead and do that. Or we might stick with our normal final exam time on Thursday. It will not be a comprehensive final. Don't fret. It should include a topic of cold work, hot work, recrystallization, which is actually all one set of lecture notes, and then steel heat treating and metallurgy, which will pretty much just be another set of lecture notes. So we'll try and cover the last week of class after our last homework quiz. We'll try and cover two solid sets of lecture notes that may actually get broke up into two or three three or four videos, but this should cover us for the next homework quiz. We're going to charge ahead, and I'm going to try and get this content covered that I think is important and can be on the FE exam if you're still facing that at some point. Let's see. Yeah, we're going to miss a topic called phase diagrams. We just don't have time to get it in. I think of all the remaining content, that is the least critical and the most theoretical and the least applied. If you're going to end up taking me for something like metals casting or heat treating later, I'll end up going over those. They may be relevant in like a metals manufacturing environment. Take thermo, you at least see like the water phase diagram. It's not quite the same, but it's something. Send me questions as you have them. Good luck and hang in there.